You know, one thing that's always boggled my mind is just how much of our world has electricity in it. So I've always been really fascinated with little devices like this. Like, this is just a charger for an iPhone or a camera. But there's an entire city on the inside of this thing. You know, it looks like little buildings. As a kid, that always fascinated me. And as I got into electrical and started to realize what was going on, there's a ton of things happening in these little charging blocks. And a lot of times we just throw these things away. But it's like really amazing that it utilizes AC and DC. And sometimes it goes from AC down to DC, back to AC, down to DC. There's just so much going on with this stuff. So today we're going to talk about AC and DC.
Make sure you stick around to the end of this video, because at the end I am going to do a demonstration of AC and DC, both with lighting, and show the differences.
So we've got AC, which just means alternating current, and we have DC. If we were to graph the movement of electrical current through a circuit, we would have our actual voltage, and then we would have time. With alternating current, we have a positive and a negative polarity because current is always going back and forth. All of the electrons or electric charges are moving back and forth, kind of vibrating. Whereas in direct current, we have voltage, we also have time, but current is always going in one direction. So how we graphically represent these is DC only has one polarity. It never dips negative. If current is traveling in one direction, we can call that a positive polarity. It's always moving in one direction throughout the circuit. If we were to switch polarity and say, you know, if this is positive and this is negative, it would no longer be positive, it would be negative. But notice, it's not a wave, it's not constantly changing back and forth, positive, negative, positive, negative. However, with alternating current, we have a waveform, and some of you may have seen a sine wave before. And all a sine wave is a graphical representation of circular motion. So if we've got a thing spinning around an axis and it's going all the way around, it starts out at 0 degrees and it goes 360 degrees, we can calculate that 360 degrees of motion and represent it on a two-dimensional graph called a sine wave. So this is 360 degrees of motion. That means this is 180, which means this is 90, and this is 270. It's just 90-degree increments. 9 times 4 is 36, that's 360 degrees of motion. So what's happening with alternating current, when I said everything moves one direction and then goes back, we go a full 180 degrees before we stop, and then we start going back the other direction. So as we go along this graph, we can imagine current is going from 0 to 90 to 180, then going back 270, 360, which is also 0. And it keeps doing that, 90, 180, 270, 360, and it just keeps going back and forth. So the fact that we have current that can alternate is really, really useful in some environments, but the fact that we have current that does not alternate is also highly, highly useful in a lot of different environments.
Did you know that because of alternating current, most of the lights and TV and computer monitors around us are blinking really fast, but our brains can't pick up that frequency. So our brains constantly think that the light is solid, but what's really happening is everything is fluttering really, really fast. So there's a thing called the fusion flicker threshold, and that is the range of which our brain can look at a frequency and tell us that it is constant when it's really pulsing. So if we were to lower, instead of using 60 hertz power systems in the US, if we were to lower it to like 20 or 30 hertz, we would see the blinking from all of that light. But because we use a 60 hertz system, we can't tell that it's actually blinking. And this is also the reason why a lot of computer monitors go up to 120 hertz, 144 or 240, because the faster it goes, the less perceivable it is to us. So now you know.
Now these devices are something that are very unique to alternating current. So these won't work with DC, but this is a transformer. They're both transformers. This is something you're probably gonna see in your house connected to a doorbell. It's got input and it's got output. The input and the output don't touch each other. So they're kind of set up like this, in a way where our input comes through one of these coils and our output goes through another one. There's some like magical, mystical stuff that happens. Not really. But when you have electrical current that's going back and forth and alternating, you can make an expanding and collapsing magnetic field around the conductor. If you have DC, this doesn't happen because you just have current going in one direction, so it's not constantly changing to force a field to expand and collapse around the conductors. So transformers allow us to change voltage, and that's why we use them in AC circuits. If I have, let's say, 240 volts and I want to feed 240 into this and I want to get 120 volts out, I can use a transformer to do this. So it takes a high voltage in, gives us a low voltage out, or it takes a low voltage in and a high voltage out. It can be used in reverse of each other. But essentially on the inside, what's going on is, since there's an expanding and collapsing magnetic field around this wire, when we have alternating current flowing through it, every time that field expands, it is picked up by this coil. Anytime you have a magnetic field and you bring it near wires, any kind of electrical conductors, it actually induces current flow through that conductor. It actually shakes up the electrons inside the material, and any free electrons that are in it will move. So that's kind of the cool thing, is since we have current flowing through and those electrons are moving back and forth here, and it's making the magnetic field expand and collapse, it's so close to the other one that that field will reach over and bump the electrons in the other one. It makes those move as well. That's how transformers work. So some transformers you'll see where there's coils side by side. There might be 3 of them, and if it's a 3-phase transformer, you'll have 3 coils side by side, but you can also have coils inside of each other. So when you put them inside of each other, when I was saying that there was a expanding and collapsing magnetic field, well, you want to capture, most of that field that exists, it goes all the way around the conductor, right? So as there are all of these lines of force around this thing, all the ones on the outside don't really do much, but the ones on the inside are focused really tightly. So we have a strong magnetic field on the inside of this because they're all collecting together in the middle, and then it's a little bit weaker on the outside. So if we take another coil and put that on the inside, the strength of the inside of this magnetic field is focused on this coil. So it's just a more efficient way of doing it, whether they're side by side, and you only have the fields that go on this, left side of this one and right side of this one, or if you try to capture all of it so that everything inside touches everything inside of here. There's just different ways of accomplishing the same thing. Now, one thing that this does not have that these do is these have an iron core in the middle of them. So if you have 2 coils like this, you can make magnetism happen on the insides of these coils, but it's not very strong. So if you add an iron core to the inside of this, you can actually strengthen that magnetic field a lot. So these, if we turn them sideways, they actually have a bar on the outside, a bar in the middle, and a bar on the outside. So these are both wrapped, the inner one's wrapped around that bar in the middle, and then they just take another winding and they wrap around that. There's an insulative layer in between them, so that they're actually not touching each other, but it allows you to wrap 2 different coils around one common iron core, and that iron core is going to strengthen those magnetic fields, and the transformer is going to work a lot more efficiently. So a lot of people think that AC is way more dangerous than DC, or DC is more dangerous than AC. They're both extremely dangerous to work with. So specifically working with batteries or DC motors or DC power generation, it can kill you dead just like AC can kill you dead. So one of the things, if you ever travel, you realize that they say lithium ion batteries you're not allowed to bring on a plane, right? Or if you do, you have to pack them with you in the pressurized cabin because it's the same pressure that our heads can handle and our bodies can handle. But you can't put lithium ion batteries under planes. So the reason for that is that lithium ion batteries are a high energy density battery. So they're really, really dangerous because they have so much energy in such a small place. So there's a thing called thermal runaway. And what happens is if a battery, specifically a lithium ion, gets too hot, it can actually have a chemical reaction inside which will heat up even more. And then there's a runaway that happens where it can cause so much heat and pressure that it explodes or catches on fire. So the thermal runaway is something that you can't really
get a hold of. And if there's more lithium ion batteries in the area, it can just exacerbate that problem. And then you have a runaway problem that you can't stop. Another danger with batteries is thinking about whether or not batteries are in series or in parallel. So when you have a whole bunch of batteries in series with each other, you increase the voltage. So if you have a 1 volt battery and a 1 volt battery and you stick them together end to end, that means you have 2 volts. So when you have a whole string of batteries and you're at some data center or something that has UPS backup power, you can have a tremendous amount of voltage. Or if you have a situation where you're running them in parallel, the voltage is always going to be the same, but you're adding amperage. So the capacity of how much fault current can travel through a circuit is huge the more that you start stacking batteries in parallel. So if a battery short circuits, you could have tens of thousands of amps, like in a car battery, if you short circuit that, and that's crazy dangerous. But if you start adding batteries in parallel, then you're increasing the capacity for more fault current for every single battery that you install. And the last thing is HVDC is kind of a new buzzword people are talking about, but it's high voltage DC. And it's something in transmission specifically. So a lot of people think only AC is traveling miles to power something, but there's actually DC at high voltages, at hundreds of thousands of volts that are still being used. So just as much as high voltage AC is extremely dangerous and can kill you and cause catastrophic danger, high voltage DC can do the same thing. So just when people are telling you DC is not as dangerous, they have no clue what they're talking about. DC is still very, very dangerous. So be safe out there.
Are you a super nerd electrician like me, where you like reading books and talking about theory and all watching videos and stuff like that? You should become a member of electricianu.com. So membership has a few different benefits. You get all practice exams that we make for free. We've got a residential wireman, a journeyman, and a master. We also have a thing called the Code Cannon, which is 300 questions, and it's not timed, it's self-paced. Take it as many times as you want. And for all of our members, every single month we put out new premium content. So a lot of videos like this that do not get put on YouTube, they're just private for our members. And then we have courses that we drop every month. So every single month we have some new course. It could be transformers, motors, motor controls, calculations, all kinds of stuff, but they're self-paced, so you can kind of go through them whenever you want. So if you're interested in nerding out like I do, check out the link in the description below where it says membership and come join us. All right, so let's go a little bit crazier into something as silly as this. This is going to use AC and DC, so let's figure out how it does it. We're just plugging this into a wall, right? Into 120 volts into a 60 hertz system. And then it does a bunch of crazy stuff to just get 5 volts of DC out. But we just said that we can't transform DC from one voltage to another voltage, and we can't put AC into a device, into these specific devices. So we not only have to change the whole AC down to DC, but we got to change the voltage that it's happening, and then we have to clean everything up. There's a bunch that's involved with it. So at first we have 60 hertz, 120 volts that we're feeding in, right? We've got a clean sine wave that's coming into this thing. So the first thing that we have to do is change that AC into something that looks like AC by simulating AC. So we bring that AC power into a rectifier, which a rectifier just takes AC and changes it into DC, but it's pulsing in a signature pattern that makes it look still like it's like a sine wave. So it's a whole bunch of pulses that make it look like AC, but it is DC. From this point, we're DC all the way, but we have a simulated AC that we're really just in DC, trying to make things still be able to move and transform. So now that we've got the pulsing DC, we have a stepped down simulated 60 hertz, 120 volt signal, but now it is DC. So what we have to do is we have to bump that up to high frequency. We want to get it really, really, really fast so it's just consistent and constant. So we bring it through a device called an SMPS, or a switch mode power supply. And a switch mode power supply basically just takes some sort of input and it switches it really, really, really fast. So we can bring it up to like 2 megahertz, kind of just depends. It could be 1 megahertz, it could be hundreds of thousands of hertz, millions of hertz, just depends on the device. But now we've got a high frequency simulated AC. Once we have that high frequency simulated AC, we're going to take that and transform it down. Now, the importance of all of this is we can't take DC and step it down. We can't transform down. That's why we still have to keep the waveform so it looks like AC. Really, it's just pulsing DC. So we take that pulsing DC, which is still a simulated AC, we step it down to 5 volts. And because it is pulsing like a waveform, there's still an expanding, collapsing magnetic field, although it is just a DC supply of power at this point. So now we're transforming it down to 5 volts. And so we still think that it's AC, but it's just pulsing DC. So next we have to rectify that and get it to stop acting like AC and just get regular DC from here on out. So we go through a rectifier again, and a rectifier usually takes AC in and converts it to DC, but it doesn't know the difference. This is still just pulsing DC, which looks like AC. It's just at 5 volts now. So now we're bringing this in and we're getting a more consistent DC, and it's still going to be a pulsing DC. It's just because it's being rectified, it's pulsing in one direction. It's no longer going to be a positive, negative where it thinks it's reversing polarity. So now we have a rippled or pulsing DC. It's not a consistent, like constant DC like you would see out of a battery. It's more of a rippled type of thing, but it's unidirectional. So it's still just current flow in one direction. It's just kind of rough current flow. And there is a maximum and minimum. There's still a pulsing that's happening. So we have to smooth that out and make it look a little bit more like a consistent, constant DC. So the next thing we do is we go through a smoothing process. We take a capacitor, and capacitors, as we know, can shift a waveform. So because they store energy, that you put energy into it, it stores it and releases it. So it actually takes this pulsing and shifts it a little bit, and it smooths out all these ripples. So now we have an even less ripply, it's still ripply, but it's nowhere near as ripply. It's just smoothed out. So now we can make a device think that there's a constant DC, even though technically it's not actually constant. So the last thing that we have in this device, there's actually several other things. There's probably some like overcurrent protection, surge protection, things like that. But we have now a 5 volt semi-clean DC that is going to trick a device enough to think that it's just regular DC, and that's where the USB comes in, and the USB puts that out. Now, typically a USB, there's going to be 2 signaling wires that can go back and forth, positive, negative, and then there's going to be power, something that you can send actual 5 volts of power to something to charge it. But a lot of the devices and the chargers are able to talk back and forth to each other, and they can kind of self-regulate to figure out, well, that's this kind of a device with this kind of a charger, so we want to make sure we only have this much current going in to charge it, otherwise they would destroy devices. But that's essentially the whole thing. There's tons of brands that have a little bit different ways of doing things. The voltage regulation is different. Sometimes they don't have switch mode power supplies, so every one of these is going to be slightly different. But just in general, the whole idea is that all of that craziness is being figured out, and the parameters are being engineered into such a way that we have this little thing that we get so irritated with. And when one of the components go bad, we don't realize all you gotta do is just unsolder it, put a new one in. We just throw these things away, and it's like, dude, this is like cosmic magic. It's just so cool that AC and DC both have such a huge impact in every single thing that we use. Literally the cameras that I'm talking to you on, the mics that I'm using, the computer, the screen, like there's so much going back and forth between AC and DC that they make up everything in our reality that we use in electronic form in any way. So for code, most electricians are pretty aware that the NEC is largely AC based, but there's a lot of DC codes in here as well. So if you look in Article 690, for instance, it talks about solar PV systems. So if you do a lot of solar work, really recommend that you look into this stuff. For instance, 690.7 talks about the maximum voltages that we can use in DC in specific settings. So for instance, if you're in a dwelling, something that's habitable where somebody can live, you can't be more than 600 volts DC. 690.11 talks about arc fault protection for DC circuits. So a lot of electricians don't even know that you have to arc fault DC stuff. If you look in 690.31 D1, it specifically talks about using metal raceways. So you have to put conductors, if you're over 30 volts or 8 amps on those conductors. You can't just run free conductors, you actually have to put them in conduit. So make sure that if you are anywhere around doing anything with DC circuits that you understand the code for DC. All right, so now to show the differences with AC and DC, what we have here is an AC circuit going into an incandescent bulb. Ouch, that's really hot. We have a LED bulb coming into AC, but the LED bulb is using AC and DC. And then we've got a battery set up with a 12 volt bulb. So both of these are 120 volt bulbs. This is a 12 volt. So I had to get a small bulb just because there's so much resistance in here that these batteries won't light the bulb up. So I had to get 12 volts. So what I want to show is the flickering effect versus the not flickering effect with DC, and then talk about how LED uses AC and DC, but there's still a flickering effect. So I'm going to turn all the lights off just so we can see everything better. All right, so let's start out with just regular AC. Now, as you can see right now with my phone recording at 240 frames a second in slow-mo, you can see the flickering actually happening. Now, I can't see it here in person with my own eyes. It looks like it's solid to me. But if we do slow motion, we can actually see the pulsing, the positive, negative, the constant change in polarity from the AC. So that's what the light bulbs are actually doing. It's just doing it really fast. Now, let's move over to DC. So with the DC setup, you notice there's no flickering, right? This is just straight current in one direction. It's clean, there's no pulsing or anything. So it is going through this bulb cleanly. Now we're gonna put this LED bulb in, which LED is again just a diode. It only allows current to go through one direction. That's what a diode does. So what we're doing is taking 120 volts in, that's AC power, we're converting it to DC through a diode and then rectifying it so that we have a pulsing that's in one direction rather than alternating directions. It's just going in one direction, stopping, then going in that same direction, then stopping over and over and over. So even though we are DC, we still notice the pulsing effect on the bulb because it's a pulsing DC. It is not a clean battery powered constant DC. But we're not battery powering all of the LED lights in our house. We're using AC. It's just trying to go through a process of converting it to DC and then using that forward only current that's rectified to create a pulsing DC. And that way the bulb will still light up and we can still use a semiconductor inside for LED output. So I hope that helps you understand a little bit about the differences between AC and DC. They're both so widely used and honestly used together more than anything else in our industry. You got to understand both of them as an electrician. You got to respect both of them as well. So love you crazy people. Thank you so much for your time, and I'll see you in the next one.